Okay, right. So, in the previous video, what we saw is that this enzyme, glutathione S-transferase, will bind to glutathione to form this intermediate here. Okay, and if there's no molecule for it to transfer the glutathione onto, it will just remain bound. Now, we can use this, I claim, to assay whether synaptotagmin, the cytoplasmic domain of synaptotagmin, specifically the C2b domain of synaptotagmin, binds to the adaptor protein complex 2. Okay, right. So, basically, if you are a researcher, what you can do is go into a catalogue and you can order tiny little beads. And I mean tiny. These are not the sort of things you played with as a child. These are tiny beads. A few micrometers, if that, across. They are tiny. Absolutely tiny. They will smaller than a grain of sand. They are tiny little things. And you can get these beads which have glutathione molecules stuck all over them. Okay? So these beads are absolutely covered in glutathione. So you can go to a catalogue and you can buy beads which are covered in glutathione. Right, what we know is that the glutathione S-transferase enzyme will bind to the glutathione. Okay, so what we can now do is we can add on the glutathione S-transferase enzyme. So we'll say this is our glutathione S-transferase enzyme here. We can bind that to the adaptor protein complex 2. So we can make a chimera of the glutathione S-transferase enzyme and the adaptor protein complex 2. So here is the adaptor protein complex 2. Okay, so let me draw the appendages this side. Okay, and I don't know actually which side you attach it on, but this is the principle. You make a chimera of the adaptor protein complex 2 and the glutathione S-transferase. So let's say it's linked up like that. Okay? And here are the mu and the omega adaptin proteins in the middle. So mu in blue, omega in red here. Okay? Sorry, not omega, sigma. Sigma, the sigma adaptor protein in red. And the alpha adaptin protein in orange, and then finally the beta adaptin protein in pink here. Whoops, okay, there we go. So, they overall are the adaptor protein complex to the AP2 complex. Now, what will happen is that when we mix the bead, which has our glutathione bound to it, with our chimera of the adaptor protein complex 2 and the glutathione S-transferase enzyme, the glutathione S-transferase enzyme and the glutathione will become linked. Okay, so we now have the beads with the adaptor protein complex 2 bound to it. And the reason I went through this all of this discussion of glutathione and glutathione S-transferase is simply because you can buy beads with glutathione attached onto them. You can't buy beads that specifically have adaptor protein complex 2 bound to them. So instead, when you're doing this experiment, what you have to do is you have to buy the beads with the glutathione bound to them, and then you have to bind to your protein the glutathione S-transferase enzyme, and that way, indirectly, you can get beads with the AP2, the adaptor protein complex 2, bound to them. But in essence, all we wanted really was the bead bound to the adaptor protein complex 2. It's just difficult to buy such setups, so instead you have to go through this process. Okay, right. So, what you are now going to do is you're going to mix in synaptic vesicles, okay, which have got synaptotagmin in. So here is a synaptic vesicle with synaptotagmin in here. Okay, now we've discussed that synaptotagmin, the C2b domain of synaptotagmin, will bind to the adaptor protein complex 2. We've also discussed that you might need PIP2 present to do this. However, PIP2 enhances this binding. It isn't fundamentally necessary. It's the case that if you get rid of it, the binding is reduced hugely, but you will still get binding without PIP2. So whether you put PIP2 in this synaptic vesicle or not, you'll still get binding, basically. Okay, right. And now what you can do is you can centrifuge your beads. Okay, so you mix the beads with the glutathione with your glutathione S transferase with the adaptor protein complex 2 bound to it, and then you mix it with your synaptic vesicles with the synaptotagmin. If our theory is correct, then we should have a huge great complex like this. What we now do is we put our test tube here in a centrifuge. Okay, so we're going to centrifuge it. And when you centrifuge, what you do is you spin the test tube round and round extremely fast. Okay, and what happens is the beads, they all drop to the bottom. So you get a pellet at the bottom which contains all the beads. Now if all of these things are bound to the beads, then they will also be in the pellet. Now, all you have to look for basically is the presence of these synaptic vesicles in the beads, which you can do by radioactively labeling the lipids of the synaptic vesicles. Okay, so what you can do basically is you can tritiumate the lipids of the phospholipid bilayer of the synaptic vesicle. So let me explain what that means. So hydrogen then. Hydrogen is the simplest element of them all. It's got a atomic number of 1. Okay, so hydrogen. Its atomic number is 1. Now the atomic number is the number of protons that you have. Okay, so it has 1 proton. Now, if it's got 1 proton, it has to also have 1 electron. So here's the proton with the electron orbiting around it here. Okay, so I'll draw the proton in red here, and let's have the electron in orange. Okay, right. Now, how many neutrons do you have is the question. Basically, that's not a question that actually has one answer. It's a question that has multiple answers. Basically, you can have differing numbers of neutrons, and you're still called hydrogen. You can put as many neutrons in here as you like, and it will still be a hydrogen atom. So hydrogen, in the definition, in order to be hydrogen, it just means that you have to have 1 proton. The atomic number is 1. If you have 1 proton, then you are hydrogen. But there's another concept, which is the mass number, which is the number of particles that you actually have in the nucleus. So this is basically the proton number, okay, so the number of protons plus the number of neutrons. So we've got 1 proton because we don't want to change what element it is. So the proton number is fixed, the atomic number is fixed. However, you can vary the number of neutrons and you remain being hydrogen, basically. So there are different isotypes of hydrogen. So, not isotypes, isotopes. So there are different isotopes of hydrogen. And all an isotope is it's these different forms of hydrogen where you have different numbers of neutrons. So one of the isotopes of hydrogen is the main one, which is protium. And this is where the number of neutrons you have is 0. So you have 1 proton, 0 neutrons. Okay, so that's what I've drawn there. I've drawn a protium hydrogen atom. Okay, this is also often referred to as hydrogen, and then you put a 1 up there to denote that it has a mass number of 1. Okay, the next one is deuterium. Deuterium. Okay, now deuterium has 1 proton and then 1 neutron. So it has a mass number of 2 because the mass number is the protons plus the neutrons. So it's often referred to as hydrogen, and then you put a 2 up there. Finally, there is another isotope that's important, which is tritium, and tritium has 1 proton, 2 neutrons, and therefore its mass number is 3, so you put H3 there. Now tritium is a radioactive isotope of hydrogen. It undergoes radioactive decay and releases radiation, which we can detect with a Geiger counter. So what we do is we use tritium instead of protium in the lipid molecules. So remember, this phospholipid bilayer here is going to consist of phospholipid molecules. So if I draw a phospholipid molecule again, here's our phospholipid molecule. Here's our phosphate head. Here's our glycerol molecule here. And here's our long-chain carboxylic acids in orange. Basically, these long-chain carboxylic acids, they're going to have a huge number of hydrogen atoms in. If we use tritium as that hydrogen in those long-chain carboxylic acids rather than protium, then we're going to get a radioactive phospholipid, basically. We're going to have radioactive synaptic vesicles. So that way we can tell whether these synaptic vesicles are within this pellet. So, let me go over the full argument again. We have these beads, which we can order in a catalogue, which have glutathione attached to them. We then take our adapter protein 2 and link it to glutathione S-transferase, and the basis of that is merely really to get AP2 attached to the bead. You cannot buy beads that just directly have AP2 bound, so you have to go through this facade here. Okay. Then what we do is we mix in our synaptic vesicles with the synaptotagmin protein in them. Now, if our theory is correct, the synaptotagmin will bind to the adaptor protein complex 2, and when we centrifuge it, these synaptic vesicles will be bound to the beads, and therefore they will be in the pellet which contains the beads at the bottom. So, we can take that pellet out and look to see whether it's radioactive. And if it is, that confirms that the synaptotagmin is binding to the AP2 protein complex. Okay, right, so what you can then do is you can take your synaptic vesicle and you can treat it with a protease. Okay, so before you mix it in with all of this stuff, you can treat the synaptic vesicle with a protease, which will break down all the proteins in this synaptic vesicle. And then there won't be no synaptotagmin left in. If you do this experiment again with the protease-treated synaptic vesicle, there's no synaptotagmin, and you find that the synaptic vesicles do not bind to the AP2, so you do find that they are not within the pellet when you centrifuge, so you don't get the radioactive signal, which indicates that the synaptic vesicles with their radioactive lipids are not binding to the AP2 complex. Moreover, the way that you can restore this binding is by returning synaptotagmin. So if you break down all the proteins in this synaptic vesicle and then return just synaptotagmin, so you don't put any of the other proteins back in, you just put synaptotagmin in, then what will happen is when you put this synaptic vesicle that just has synaptotagmin in, it will bind to the AP2 protein complex, and it will therefore be pelleted. It will come down in the pellet, so you'll have a radioactive signal from the pellet because the radioactive synaptic vesicles are there. And this sort of an experiment was done by a guy known as Sudhoff and his colleagues. So I'll just put Sudhoff et al. Okay, right. Oh dear, damn it. Sorry, I've just put a line through his colleagues. Never mind. Okay, so this is how you can confirm this interaction between the adaptor protein complex 2 and the synaptotagmin protein.